Okay, so we will now begin the award ceremony for the fellowship cohort of the current academic year. Then we'll have a musical interlude by the Baroque Ensemble, and then we'll continue with the award ceremony for the fellowship cohort of the next year, the forthcoming academic year. Each fellow will be invited to deliver a short lecture describing their project, their interests in science, and at the end of which they will receive their certificates, and the check comes to the bank account, as far as I understand, not here. So you still have to work for it. And then we will conclude with a tribute to the Root Unknown Fellowship Program, which will be discussed later. And but this Root Unknown Fellowship Program supports female scientists who are alumni of the Adams Fellowship Program. Okay, so we will start with the older group of recipients, of fellows. And the first one is going to be Elad Ballas from Bar-Ilan University. Elad is here.
Okay. Hi, everyone. Good afternoon. My name is Elad Ballas. I'm a PhD student in the Department of Chemistry at Bar-Ilan University, working under the supervision of Professor Ohad and Professor Doron Orbach. As a father of 4 amazing children, one of the trickiest parts of doing research while raising a family is balancing the time between the lab and home. My 5-year-old son always asked to come with me to the lab. From the story he absolutely believed that chemistry lab is where all the most amazing things happen. But as you can imagine, chemistry lab with flammable materials is not the ideal place for young children. So usually my first response is, don't get me in trouble with mom. But then I tell him something that I truly believe. The most amazing things are often the most simple. And many of them we can do right at home, in our kitchen, for example. So yes, maybe mommy still get mad. Since I was a child, I'm fascinated by how small things can lead big transformation. I try to explain to my children, even understanding simple insight like how water and oil behave can lead breakthrough in energy storage. Oh, but what is energy storage? And why energy storage becomes so important? We are all aware of the global climate crisis, which is driven in large part by greenhouse gas emission from burning fossil fuels. As a result, in the last few decades, many research focused on generating clean energy from renewable sources like solar and wind. And they're pretty succeed. But there is a catch. These sources are unstable. The sun doesn't shine at night. The wind doesn't always blow. If we can store the energy, this natural energy, when it's abundant, and release it when it's needed, we can significantly reduce our dependence on fossil fuels. That's exactly where batteries technologies come in. They are compact, they're efficient, and they are everywhere, in our phones, in our laptops, and even in our cars. But today batteries, especially lithium-ion batteries, come with 2 main drawbacks. They are expensive, and they are highly flammable. Inside the batteries, there is a flammable electrolyte solution that can explode under extreme conditions. So we try to think which kind of liquid is inexpensive and also non-flammable. The answer was easy, water. That's why I start working on water-based battery, my research. But working with water is not so simple. One of the biggest problems with water is when we use the high voltage, water decomposes into oxygen and hydrogen gases. So our goal was clear, to find the right balance where we can still enjoy the safety and the low cost from water, but also we need to increase the voltage to get high energy density of the battery. To do so, we use tiny materials with very small pores, less than 2 nanometers, that can hold a special salt. These are special salts because just under charging, they create an oily barrier between the water and the electricity. These simple tricks enabled us to double the voltage of the battery and also keep high efficiency of the battery as well. So, yes, I truly believe that deeply understanding simple insight like how water in oil behave can lead breakthrough in energy storage. I also believe that aqueous-based battery may be a very good solution to this important mission. And I also believe that our country, Israel, even we are a very small country, may be the flagship for this target. So I want to thank to Adams family. I want to thank all the Adams community, and I also want to thank to my parents and my wonderful wife, Shira. Thank you all.
Very interesting. Very interesting.
Okay. Okay. Next on the list is Nadir Boni.
Hi, everyone. It's a great honor being here and talking to all of you. And before I start talking about my research, I want to first ask you guys a question, and I'll ask it in English and in Hebrew, just in case people don't speak English here. How many of you have been in the supermarket lately and saw a lot of products that have extra proteins in them? כמה הלכו לסופר וראו שיש פתאום המון מוצרים עם חלבון? Show of hands. Okay, most people here. How many uses them daily or even once a week? Also a lot of people. I want to talk about proteins today. This is my area of research. And I want to say that proteins are not only important for our lifestyle because they build muscle, they actually are crucial for almost everything that our body does and perform. For example, antibodies, nogdanim, you may recall them from COVID pandemic. They are actually proteins, and they are specialized to fight viruses, for example. But many more things like producing energy producing energy, allow us to smell, to think, for our brain to function. All of this is because of proteins. And in fact, if you think about it, our cells can be like these very tiny factories, and the proteins that are in our cells are actually the machines that allow everything to operate in the factory, and they produce everything. So these are very complex machines. They know how to communicate with each other and talk with each other. And sometimes even these small machines can actually assemble into huge machinery that work in our cells and help us produce energy. And just like a factory, if you have a problem with manufacturing and the machines in the factory, then you get some trouble. For example, if you have a machine that works too fast or too slow or just stop working all of a sudden, then you can get something like cancer. And if you have machines that communicate with the wrong ones, you can get neurodegenerative disease, like, for example, Alzheimer. And this is why I think it's important to study proteins and understand how they work. We're doing it with machine learning and biophysical experiments. And our goal is to understand how proteins work, how they communicate with each other, and kind of reverse engineer the process. Because if we will understand how they work, we maybe can try to make them better, maybe create new proteins entirely. So if we want to fight COVID, for example, we may want to create better antibodies. Or if we want to, for example, dispose of plastic, maybe we can create new proteins that know how to do it. So I hope that now, when you go to the supermarket and you see extra protein, you not just think about muscle, but also other things. And I hope that now my research is a little bit more clear. And I want to finish by saying thank you to the Adams Family and Foundation and the Israel Society of Academy of Sciences and Humanity. And thank you all.
Thank you very much, Nadir.
Congratulations.
Okay. Next one is Amit Elad from the Hebrew University.
Good evening, everyone. My name is Amit Elad. I'm 31 years old. I was born in Kibbutz Matsuva, a few kilometers south of the border with Lebanon. And I want to thank my parents that came all the way to be with me today. Today, my partner Shlomi and I live in Kibbutz Ma'ale Hamisha, which is kind of close to Jerusalem, where I've been studying for the past decade. I'm participating in a program that's called MD-PhD, which means I'm training to become a physician, and in the meantime, conducting a PhD in Professor Dani Ben-Tzvi's lab at the Hebrew University. He's also an alumni of Adams. So being in this kind of project means I'm moving constantly between two different worlds, medicine and research. In the hospital, I rotate through many different departments. In the past year, I've witnessed labors. I've participated in C-sections. I saw surgeries in the brain, eyes, joints. I've helped ventilate patients. I examined patients with neurological and psychiatric diseases. And I also was present in very difficult conversations. For example, an oncologist who informed a 40-year-old mother that she has stage 4 colorectal cancer. And when I finish these days, I remove my medical hat and put on the research hat and head back to the lab where I deal with mice and human tissues and cells and computational data. It's very different. It's kind of strange, this movement. In medicine, you basically deal with people in their most vulnerable and intimate situations in life. And then you go to research, where you deal with principles and models and experiments and data. But I think the connection between these two is exactly the point. Research is one of the main reasons medicine can move forward. Antibiotics, imaging, immunotherapy, surgery. And on the other hand, medicine is important in guiding research to the correct places, I believe. And the questions that we ask are not abstract. When you deal with cancer, there is a family, there's a patient, there is a real clinical issue behind it. And for me, it was very concrete when I spent time in general surgery, and I saw all kinds of surgeries, including bariatric surgeries, ניתוחי קיצור קיבה, which treat morbid obesity, but they aren't just mechanical changes. They introduce hormonal and metabolic changes to the patients that undergo them, and can even lead to remission of diabetes. It was extremely interesting for me because one of the first subjects that I joined in Dani's lab was exactly this, bariatric surgery. We gathered tens of thousands of cells from humans' stomachs of patients, and we analyzed them each in order to check what changes they undergo following the surgery. Do they remember they had this surgery? And we saw that one of the major effects is the endocrine cells. Endocrine cells are cells that secrete hormones to the blood, and in the stomach, they facilitate hunger, metabolism, acid secretion, digestion. And we saw that after the surgery, they changed their identity. And we wanted to understand why this happens. But before we can understand why, we had to understand how they, in the first place, obtained this identity. And this is one of the main subjects I'm interested now in my research. I'm trying to understand how these cells are generated, how they acquire their identity, and choose which type of hormone they secrete to the blood. We use different single-cell technologies in order to map their differentiation each and every step, but observing it alone is not enough, I think. I think in order to really understand how they develop, you have to build it yourself. So this is why we are using human gastric organoids, which are kind of small stomachs we grow in the dish. So for the first time, we were able to create a controlled in vitro model to study gastric endocrine cells. And we are able to answer questions that we couldn't ask before. How these cells are formed, what might be the changes after bariatric surgery, how these cells regulate the hormones that they secrete and change our appetite, for example. What can cause them to suddenly become neuroendocrine tumors? And these are basic biological questions, but they have clinical meaning to them. And this kind of reasoning I want to bring to my future as a physician. I want to treat patients, see the tools that are lacking, and bring back questions to the lab and try to figure it out. In the recent years, we saw how important it is for Israel to have a strong medicine system, a strong science system, and strong academia institute. We must create international collaborations without hesitation, but also be able to grow by ourselves. And I want to thank the Adams family for building this foundation and allowing us to have a strong foundation for science and medicine here in Israel. So I want to thank the Adams family. I want to thank my family and my partner Shlomi and all of you for listening. Thank you.
Next one is Marck from the University of Haifa.
Hi, good afternoon. My name is Aya, and I am a PhD student in the Animal Flight Group at the University of Haifa. Yeah, I'm very excited to be here. So under the supervision of Professor Nir Sapir from the University of Haifa and Professor Izar Lavner from Tel Chai University, I study nocturnal bird migration using bioacoustics, which means the study of animal sound. As a bachelor student at Tel Chai College, I lived in Metula, overlooking the Hula Valley. Every autumn and spring, I looked forward to seeing the first cranes arriving from Europe. I was fascinated by the number and diversity of birds passing through our region, and that curiosity eventually led me to study bird migration. Migration is one of nature's most remarkable phenomena. Billions of birds travel thousands of kilometers each year, moving biomasses across continents, and influencing agriculture, ecosystem functioning, health, and biodiversity. So by improving our ability to monitor migration, we can better understand and protect migratory species. So in my research, at its core, I ask three simple questions. Which species are migrating? When are they migrating? And in what numbers? Surprisingly, these questions are still difficult to answer. So the reason is that most bird migration happens during the night, when direct observations are nearly impossible. Radar systems, in the other hand, can detect large-scale bird movements, but they cannot, even at night, but they cannot tell us which species are flying overhead. So to answer that question, I turned to the sound bird produced during migration. Many migratory birds use short flight calls while flying at night, and I'm using this information to uncover which species are flying. In my research, I deploy automated audio recorders that operate from sunset to sunrise, collecting thousands of hours of recordings. I then use machine learning models that we developed that scan the recordings and automatically detect and identify the calls into the species level. So far, we had achieved 95% accuracy on our in species recognition on our test set, and therefore we're applying this system on our field recordings collected during 2 migration seasons in southern Israel, and we applied it, and we applied the system, and we were able to reveal seasonal differences in migration patterns and to characterize species-specific phenology. This approach has never been applied before in Israel or along the eastern migration route between Europe and Africa, which is a major and important flyway. Personally, I find I'm very excited to use personally, the use of AI in my research is okay. So I'll sum up. The use of AI in our research enable us to process enormous data sets, and even more importantly, to uncover patterns that would otherwise remain hidden. So now, by combining bioacoustics and AI, our research can provide the species level information needed to better understand bird migration, how it is changing over time, and how bird species can be better protected. So thank you for your support, and thank you for listening.
You notice there's a theme. Everybody mentioned AI. Yeah. Seems to be the new science. Yeah.
Okay, and the next one is Ohad Segal from the Technion. Ohad.
So hi, I'm Ohad. I would like to start by thanking the Adams Foundation for supporting my research and my academic journey. And next, I would like to thank my parents who raised me in a small village near Haifa, next to the Mediterranean. And they are both windsurfers. So from a young age, they really wanted me to windsurf, right? This water sport when you go with the sail. But naturally, as a child, you don't want to do what your parents want you to do. So I didn't want to do it. But I did find myself fall in love in the concept of waves and surfing initially, so surfing waves without the sail. And ultimately, I did get into windsurfing, which makes them really proud. And actually, I even windsurfed with them today in Haifa. But this water sport and other kind of extreme sports that I got into because of my parents, they led this curiosity in me about how nature works and specifically how waves work. And you can imagine that after I finished my high school, I enlisted to the Navy, and I was a scuba diver there for 4 years. But after finishing my military service, I thought, how can I combine this curiosity with doing something, you know, what that everybody is expected to do once they finish the military service and study. So I started doing my undergrads at the Technion in electrical engineering and physics, which is mostly just learning, right? It's not doing research, it's not really, it satisfies your curiosity, but it doesn't let you learn something that is new to everyone, just new to you. And following that, I decided to check if my curiosity is really strong enough to do research, and I joined Moti Segev's group at the Technion for a specific project about light waves. And this project deals with controlling light, but with changing the materials in time, which is a little bit of a weird concept, and I'll try to explain a little bit how that does work. So first of all, we do not control the light using mirrors or lenses. We control the light using changing the material's properties in time, and I will give a specific example soon. But first, I will tell you why this project really appealed to me and why I decided to follow up on this. And this is because of two major applications that can be done following this research. The first is generating light using this changing in time of materials' properties in colors we cannot generate today. This is exciting for medical imaging and for security imaging. The bottleneck in these kind of applications that I'm talking about is that, unfortunately, we cannot generate light in whatever color we want. For example, take the laser pointers we have in our everyday life. They come in green, red, and purple, not in every color we want. So taking the same intuition, there are several specific colors we do not see. They have very nice applications in medical imaging and also in security imaging, but we just don't have any efficient light source for them. So doing this kind of application, doing this kind of phenomena I'm talking about, I'm exploring in my research, can lead to these light sources in the future. Also, this controlling of light using interface or using changing the materials in time lets us also control the quantum properties of light, which is very exciting for all the new buzzwords you're hearing about, all these quantum communication, quantum computation kind of applications. But now I promised you an example, okay? So I'm going to tell you, in essence, like a mind experiment of how a recent project I've done works. Okay, so this is something we have done in our lab very recently, okay? And it works this way. Think about a pulse of light. So let me build this pulse of light. And I'm propagating through this room, okay? And suddenly, somehow, the entire air in the room changes into glass. I will tell you soon how we do it in the experiment, but now just go with me. So I was going through the room, and suddenly the entire room turns into glass. Now, I didn't hit anything, okay? But still, part of this light wave goes back, like it felt this change in the material, okay? But it doesn't act like it hit a wall, turns around, and go back. It actually goes back like a video played in rewind, like it's going back in time. So we were able to measure this wave that goes backwards in space, acting like a time reversal of the original wave in the lab for the first time in light. And I promised to tell you how I changed the entire air in this room to glass. So of course, in the experiment, it's not exactly how I do it. We use a specific kind of glass, which is similar to the one you have on the screens of your cell phones. And the way we change its properties, which is the property I'm talking about here, is the velocity of light in the medium. So the way we change the velocity of light in this medium is we bombard it with another light. So actually, we have two pulses of light taking part in this experiment. One is changing the material, and the other is going through the material, feeling this sharp change, and reflecting in this very weird manner that I told you about. So I hope you liked what I told you, and if you're interested, please come afterwards and ask me as many questions as you want. Thank you.
Thank you, Ohad, for enlightening us. Okay, thank you, Ohad. And I now invite Maayan Z from the Weizmann Institute. Maayan.
Hello, everyone. So I'm Maayan. I'm coming from the Weizmann Institute, and actually, the last year's seminar, which didn't happen, was about the same time that my department building got severely damaged from the Iranian missile. But we're still here, and we're still the science doesn't stop. So when it came time for me to choose a field for my bachelor's degree, I was considering two different options. On one hand, geology, inspired by my Army service as a geographical intelligence officer. I was thinking about digging through rocks and revealing stories that are millions of years old. Okay. Surrounded by nature-loving people and people in sandals, a very natural fit for someone who grew up on a kibbutz in the Golan Heights. And thank my parents for coming the long way from there. On the other hand, my analytical nature drew me towards computer science. And I imagined myself being surrounded by students with their heads deep in code and tackling complex problems. And so you could say that I was choosing between studying the past or studying the future. And I couldn't decide, and maybe I didn't want to at that time. So I chose both, and I pursued a dual degree in geology and computer science at Ben-Gurion University. And my studies in geology, understanding structure, material, and physical processes had led me to planetary science, which is what I study today. So one of the central questions in planetary science is how planets form and evolve. And that's including our own habitable Earth. And to better understand these processes, we go to the giant planets, and especially Jupiter, which is the largest, most massive planet in our solar system, and likely the first one to form. And if we better understand its interior, we can trace back and understand the conditions of the early solar system, and also ultimately understand what led to the emergence of Earth. My research focuses on understanding the internal structure of giant planets, their layering, their composition, their physical properties, and trying to show what they can tell us about the origins of the solar system. So talking about Jupiter, we can observe it from Earth, and we can learn quite a lot from it, but we are very limited by distance, and we cannot measure what's going on deep inside. So for the past 5 decades, NASA has sent a few spies to Jupiter. Most recently, the Juno spacecraft, which has been orbiting the planet since 2016, returning very valuable data. And during my master's degree, and also now in my PhD, under the supervision of Professor Yochai Kaspi, I am privileged to be a part of the Juno science team and engaging and collaborating with leading experts in planetary science. So the good news is that we have Juno. The bad news is that it cannot probe the planets down to its core. So it can only provide external measurements. So we now want to collect the different clues that Juno provides us, and also the previous spies that were sent, and trying to, for example, with measurement of temperature, composition, wind, and trying to solve the puzzle that is the interior structure of Jupiter. Juno, and the most important clue that Juno provides us is the measurement of Jupiter's gravity field. So we can think about this information as a color. Let's say purple. Jupiter gives us the color purple. And my job as a researcher is to figure out which combination of colors produced it. Okay? Which combination of color produced it. In other words, I'm trying to say which internal structure, which layers and materials inside Jupiter can produce the gravity field we observe. So if it's a simple type of purple, the solution is easy. You just mix red and blue. But actually, Juno provides us with an extremely accurate shade of purple, and there are different combinations of colors that can get to the same result. And this is exactly the challenge with gravity data. Many different internal structures will produce the same external gravity field. So, and going over with so many possibilities, going through all of them, it becomes a very computationally heavy task. So to deal with that, AI, the buzzword, we developed machine learning models, machine learning tools to accelerate the search and simplify the problem. And this approach makes the calculation roughly 100,000 times faster. So we can actually scan much more models than that would not have been possible otherwise. And looking back, and so my research highlights that this is a very exciting time in planetary science. We got a wealth of data coming from space missions, and really advancement with computational tools and AI that we can now tackle fundamental questions about our solar system and about planetary system in general. And I want to thank the Adams family and Adams Foundation for supporting my efforts in this exciting time. And going back to my old dilemma, studying the past or the future, I'm proud to say that by combining planetary science and machine learning, I get to do both. So thank you.
Very much. Okay, thank you, Maayan. Okay. And before I forget, each of the fellows is also supposed to get a pin, which is sitting here. So the next round will get them as they go on stage. Those that already received the certificates, at the end of the ceremony, please come over and you'll get your pins. They're all over here. Okay. Okay, so before moving forward, I'd like also to recognize Yardeh Shefer from the Weizmann Institute, who was not able to be here this evening. And again, let's congratulate all the 25, 26 Adams Fellows. For their outstanding research and also for their illuminating presentations. Okay, and now let's turn the floor to the Biochemistry ensemble, and we'll hear some nice music.
שלום לכולם, זה היה לפר על גיטרה ברוק, ועוד גיטרה מיוחדת, ואני מנגן על הכלי הזה, זה דיברתי גם אנחנו נגן לכם שני קטעים, יצירה מאת סילבן, יצירה ברוקית, במאה ה-18, זאת סונטה למיולה גמבה בגיטרה. אנחנו נגן ברצף את כל הפרקים. סילבן בחר בכלי הזה כדי לתת לו סונטה שהיא בעצם נשמעת כמו קנטטה, זאת אומרת לא צליל אלא שירה, שירה דרך הכלי הזה. אתם תזהו שהמוזיקה דומה לאריה, מאופרה, רציטטיב, ובסוף איזשהו פרק עליז שנשמע ממש כמו משהו שם בכלל. ואחרי זה אנחנו ננגן לכם עוד שיר שיציג אחרי זה, יותר מאוחר, שיר ישראלי שהמקור שלו הוא בלבנון.
השיר הבא הוא ממש מגיע מאיתנו, מהמסורת שלנו, מהיהדות שלנו, שיר מאוד מאוד עתיק שבעצם מגיע מתרבות הלדינו, השפה שבעצם ייחדה את כל יהדות ספרד, אחר כך גם פורטוגל, כל האנשים שאחר כך נפוצו בגלל גירוש ספרד. השיר נקרא במקור מאמיון פדרוביסטו, ואחר כך הוא הפך לממש גרסה ישראלית בשם התרגעות. יש כאלה שאפילו מכירים אותו בשם מי יש אי שם. בכל אופן המנגינה אני בטוח שאתם מכירו אותה.